Hello, my name is Neville Hogan, and I'd like to tell you about some of the work we've been doing to try to understand the controller underlying those interesting results that Megan Huber presented. Let me share a screen. So the particular approach that we've been looking at is the consequences of mechanical impedance compositionality. And let me give some context here. So it's very clear that humans are capable of spectacular performance, but what's not so clear is that they have inferior hardware. We can manage a body with more than 200 degrees of freedom. Not only that, but we can manipulate infinitely complex objects like whips and ribbons. But we do that with very slow muscles. Muscle bandwidth is substantially less than 10 hertz. Very slow neurons. Neurons communicate at about 100 meters per second at most. And severely delayed feedback. The transcortical feedback delay is greater than 100 milliseconds. And there's some evidence that in posture imbalance, the delay is as much as 300 or more milliseconds. So we've got a slow system, but we are able to perform very well. How do we do that? Well, the hypothesis, which is what Megan presented, is that the humans use dynamic primitives to work around neural limitations. And we think this is worth studying because studying humans may facilitate improved robot control, improved physical human-robot collaboration, and this is important, facilitate the scale up to many degrees of freedom. The idea, of course, is that dynamic primitives, as Megan explained, they are attractors of low-level dynamics, such as, say, a limit cycle oscillation or mechanical impedance. And these pieces are combined in a nonlinear generalization of the classical equivalent circuit from circuit theory. The key point about mechanical impedances is that they have this property called compositionality. And that means that impedances superimpose linearly even if they are nonlinear. And this is actually nothing more than the fact that the impedances generate forces as output. And if the impedances are connected to an inertial object like the linkages of a robot, then the linkages just add up the forces. We can use that to solve some otherwise tricky problems. For example, managing redundant degrees of freedom. Consider, for example, if we have a desired task space stiffness, which I have written down here. This is a task space stiffness. I can map that to configuration space using the forward Jacobian and the forward kinematics. I can then define and that controller will then implement the desired endpoint stiffness. However, it will not manage the redundant degrees of freedom in the robot. But to do that, I can define a configuration space stiffness or impedance, which is essentially a stiffness that tries to drive the linkages to a nominal equilibrium configuration here, theta with the subscript n. To manage the redundancy and to perform the endpoint task, I simply add those two up and now have a way to manage redundant degrees of freedom while achieving endpoint behavior. The important features of this is that, first of all, there are no inverse kinematics involved, so the computations are relatively simple. Secondly, it allows a modular approach and can manage a number of different things that are important. For example, it can manage a flexible object. In the video, I'm showing some work done by one of my students, David Verdi, to get the Baxter robot to do shoe shining. And that means that the Baxter has to pick up a cloth, it then tensions the cloth, it then moves it into position and applies a normal force, and then applies a sinusoidal oscillation. Now, this is a relatively straightforward application, but it shows that we can manage multi-arm coordination, contact and non-contact phases using this approach. The important thing here is that this readily extends to 2 or more arms if they're connected at a common endpoint or if they're interacting with a common object. Basically, the net endpoint stiffness is the sum of all the components. I can superimpose open chain single arm controllers. For example, here's one for the left arm. It's what I showed you previously. But I do the same sort of thing for the right arm, as I showed you previously. And I just run those in parallel. Their forces add up. And I wind up with a means to handle closed chain kinematics with no closed chain kinematic computation and no inverse kinematic computation. And that latter is important because we show here in this video, again from David Verdi, that the robot is able to go all the way into a singular configuration. And importantly, it's able to come back out of that singular configuration seamlessly and get back to the configuration that it started in. So the idea here is that the composition of dynamic behaviors avoids challenges. And the reason it's important is because using these dynamic primitives may require minimal central control, and that is, it's a reduced need for continuous intervention, yet achieve high performance. Each primitive is itself a highly dynamic behavior. But of course, as every engineer knows, there's no free lunch. So that means that using dynamic primitives may also imply limitations. So one of the drawbacks of impedance composition is the potential task conflict. So the task and configuration space equilibrium configurations may conflict. So the configuration space impedance controller drives the system towards an equilibrium configuration denoted theta sub n. But if we don't solve the inverse kinematics, we have no idea whether or not that the corresponding endpoint or task space configuration corresponds to the one that's specified by the task space impedance. So those two may conflict. An alternative approach is to use null space projection. That is, project the configuration space impedance into the null space of the task space impedance. This is standard computation. You use that by figuring out a Jacobian pseudo-inverse. Use the Jacobian pseudo-inverse post multiplied by the forward Jacobian, subtract the result from the unit matrix. That gives you a null space projector matrix. And you then take the configuration space stiffness and pre-multiply it by the null space projector. And what that does, it means that the configuration space stiffness only operates in directions that do not conflict with the task space impedance. This does have a drawback in that it gives you a non-passive behavior, and that means that coupled stability may be compromised, but it does eliminate the task conflict. So we tested this in some experiments. The experiments used an impedance-controlled 7-degree of freedom robot, which was coupled through a universal joint with essentially zero friction to a highly backdrivable 2-degree of freedom planar robot. And we had a force torque sensor on the planar robot to measure the interaction forces. We programmed the 2-degree of freedom robot to simulate motions that were without a constraint and motions with a circular constraint, like turning a crank. And we did that under two conditions. One in which the task space at 6 degrees of freedom, that is, the specified motion was both position of the robot end effector and orientation of the robot end effector. That left a 1 degree of freedom null space. The second condition was in which we used a 3-dimensional task space. That is, only the position of the robot end effector was specified, and that left a 4 degree of freedom null space. What we found was quite interesting. First of all, in the case where we had a 1 degree of freedom null space, we clearly showed with the mid-range stiffness that we chose for the joint, the configuration space stiffness, we clearly showed task conflict. So the dashed line here is the nominal circular path. This is the unconstrained case. And we can verify that because the force here down in the bottom left is essentially 0. But you'll notice that the blue trace, which is the superimposition of impedances, it substantially deviates from the desired path. In contrast, the null space projector case, it follows the desired path quite well. There's a small error probably due to inaccurate kinematic calibration, but essentially the null space projection works. The surprising thing was when we went to a 4 degree of freedom null space, that we found that in that case, the superimposition, the impedance superimposition approach worked as well as the null space projection approach. And again, this is unconstrained motion, as you can see from the normal forces. And the difference in performance between the superimposition and the null space projection approaches were essentially 0. In fact, they were statistically insignificant. We go look at constrained motion. In this case, we programmed the 2 degree of freedom robot to emulate a circular constraint. That's shown here with this dotted line. And the circular constraint is inside or of lower radius than the nominal path, which was the heavy dash line. And what you can see is that because the constraint is simulated with a high stiffness but not an infinite stiffness, you see that the robot controller will bring the path to a location somewhere between the zero force path here, this is the heavy dashed lines, and the constrained path. And as before, the null space projector works reasonably well. Some small errors here, but quite good. The nominal force that we expected was here just above 20 newtons, and the actual forces that we see are not too far from that for the null space projector. But in the case where we have the impedance composition, we get substantial errors. Not only that, but in some regions, the superimposition case generates compressive forces on the constraint. And that's potentially concerning because that could be unstable. However, when we go to the 4 degree of freedom null space, we find that the superimposition of impedances does essentially as well as the null space projection. Slightly poorer, as you can see here, but if you compare the data, the difference is extremely small. Another thing to point out is that these results were obtained with a mid-range value of the joint stiffness. If we use low configuration space stiffness, that also reduces the task conflict. In this case, both in the case where we have a single degree of freedom null space dimension, in that case, we find that the null space projector does quite well and the impedance superimposition does almost as well. We go to the 4 degree of freedom null space and we find that the performance is essentially identical. So if you look at the unconstrained case and the constrained case, we find that there's no difference that we can detect. So what does this mean? First of all, I think that it's clear that many degrees of freedom can present a substantial computational challenge using conventional approaches to robot control. For example, if you use motion control approaches, you've got to solve an inverse kinematics problem, and that's solvable, but computationally difficult, especially when the number of degrees of freedom becomes large. On the other hand, humans operate many degrees of freedom all the time. Well, if you take this approach exploiting mechanical impedance compositionality, first of all, it enables a modular building block approach. That is, you can manage the redundancy in one block and the task space behavior in another block, and yet another block to manage, say, the left arm or something like that. And this approach clearly scales up to a very large number of degrees of freedom. It can manage challenges like singular configurations, closed chain kinematics, high degrees of freedom, high degrees of redundancy, all with very little computation beyond that required to manage a single arm. So it turns out that many degrees of freedom may be a blessing rather than the curse of dimensionality that Bellman spoke about. So let me thank you for listening.